as was mentioned, I work at the National Museum of Computing, and one day before we opened to the public, I was wandering around the museum and I saw this poster on the left-hand half, and it speaks about, or it writes about, one Kateryna Yushchenko, who was a well-known programmer, Ukrainian programmer. This talk's going to have a number of topics. I'm going to introduce you to Kateryna Yushchenko. And then I'm going to talk about a programming language that she invented and another programming language that she sort of invented. And then I'm going to talk about the KIEV or KIEV computer and its programming language, and also a deeper look at the address programming language, topic number 2. So Kateryna's dates were December 8th, 1919 to August 15th, 2001. And she earned a PhD from the Ukrainian Academy of Science, making her the first woman in the USSR to become a doctor of physical and mathematical sciences. She was a member of the team who developed MESM, first fully operational electronic computer in continental Europe. There's probably debates about whether or not it's really the first. I'm just quoting the poster. In Ukrainian, it's actually called an MEOM. Her most famous contribution is the development of the address programming language, or APL for short, not to be confused with the other APL. Let's look at her name briefly. In Ukrainian, her name is Kateryna, but in Russian, it is Yekaterina. So she has 2 names, 2 first names, different first names. If you look at the book which I'm going to discuss briefly, you'll notice the first letter of her name is an E. And even if you don't particularly speak Russian, you can really see that it's an E. She was also involved in the publication of a book called Address Programmovanie, which is the address programming language, and also another book, Elementy Programmovanie, co-authored with Gnedenko and Korolyuk. And I'm just going to comment that her name is last on the list. That's not necessarily because she was the least significant author, but in the Russian Cyrillic alphabet, the first letter of her name is the second last letter in the Cyrillic alphabet. So they were just going in Cyrillic order. He's got the last, he's got the short straw, so to speak. The general principles of this programming language is that it introduces what Google Translate unhelpfully gave me as the principle of targeting. It basically means having addresses in your program instead of just having constants, which is a concept I'm sure we are all perfectly familiar with, because even computers like the EDSAC and the WITCH have data being pointed to by addresses in their instructions. An example of the address programming language is prime B goes to A, which is equivalent in C is just A equals B. So it means the contents of B get moved into A. There's a bit of Pascal there, but I don't particularly speak Pascal, so I will stick to the C side of the thing. There's double prime A goes to B, which is effectively B equals star A. Triple prime A, which is C equals star A. Double prime A is also in some documentation which I've been reading is written as a 2, upper shift 2 A goes to B. And then there's there's this which I can't really read because it's covered with somebody waiting to be admitted to the waiting room. So basically we have here, it's you can, instead of having a positive number before the A in the previous examples, you could have a negative number, which means that you can get an array of data containing the item that you're looking at, or an array of pointers containing that point to a memory location that contains the value you're looking for. This operation has no direct equivalent in modern programming languages, source, says Wikipedia, and it can be expressed in the form of the following pseudocode, which is basically just going through an entire array of data and adding it to an empty array containing the value you're looking for. If you want to know more about the address programming language, then I suggest you Google address programming language Wikipedia, set Ukrainska from the list of languages, and use Google Translate on the resulting page. Or the fourth thing is you can stick around here, so I'm going to go into the address programming language in somewhat greater depth later on. These are the four versions of Elementy Programowania. This one is clearly the Russian version. Our participant has enabled closed captioning. This is a French translation for which I was extremely grateful because it's way easier to follow a French or indeed a German translation, Elemente der Programmierung, than it was for me to read the Russian one. And there's also a Hungarian version, Bevezetes Programozáspa. So there's four versions of this book in effect. The original published in 1961, and then German and Hungarian translations in 1964, and French translation in 1969. And the Russian language version covers 5 computers: the Besem, the Strela, the Ural, the M3, and the KIEV, as it was called at the time. And but this list varies for different translations. For some reason, the Hungarian version includes the Eliot 803, of which we have one at the National Museum of Computing, which we run, and a special person who knows how to run it. These books describe a pseudo-programming language which you can use to program any of these machines, given a suitable interpreter. Data is held in floating point. Every order has 3 addresses, and there's a pseudocode, which I'll come into shortly. This is a picture of the Besem, which I took at the British Museum. Just need to close a thing here. It doesn't run, as far as I know, or if it does run, possibly nobody knows how to run it. I've never seen it run. And this is the first program in the book, Elementy Programowania, and it's quite a simple linear formula: y equals ax plus b divided by cx plus d. But more interestingly is how the program is described. So we have this is the data of the program, and it has 7 memory locations, alpha 1 through alpha 5, and then omega 1 and omega 2. And their initial values are A, B, C, D, and X, and then the final value is in Y. And this is the program itself. You can see, I don't quite know why, but all the programs seem to start at address plus 1, not what I would expect, which should be address plus 0. The second column is the actual operation code. So you've got a multiplication, an addition, a multiplication, addition, a division. The capital pi is a print. And then the last instruction is an OCT. I know it says OCM, but it's actually an OCT because the curly Cyrillic M, the T, as opposed to the angular Cyrillic M, which is an M. There are 3 different alphabets: Latin, Cyrillic, and Greek. So the editor of the Resurrection might be very pleased to know that I'm not planning to submit an article about this. Having already given him enough problems with the Greek and English INSAC paper. Now, I thought that program was rather simple and I wouldn't waste any more time on it. So I went to a slightly more complex program, programmer number 10. And I showed this to one of my colleagues at TNMOC, and he immediately said, well, clearly that's a square root program. And indeed. So in the left column, you have, once again, data values. And in the right 4 columns, you have the instructions, which starts with a divide, and then there's an add, and then a multiply, and then a subtract, then a plus. And then this is a less than using absolute values rather than signed values. And then another OCT, which I should have said is a halt instruction. I then wrote this into a notepad using the appropriate Greek and Latin and so on. And then I wrote yes, this is just a brief explanation because you probably don't need, you probably all know how to do square roots by approximation, Newton-Raphson, where A is the number for which the square root is being sought. And you start off with a guess, which can be any number you like, as long as it's less than the answer. So you can start with 1. And this is a program written out. Data first, then the program itself. And I've added an extra instruction at the beginning, which is a capital V, lowercase v, which means read cards. And then it goes off and runs. Then I wrote a simulator to actually execute this program. And you can see that I started off with the value of 2. Down here, does my mouse come up on there? Yeah. Yes, good, thank you. The square root of 2 is, as every schoolboy knows, 1.41, 1.444, and so on. I then squared that value just to make sure I got an approximation to the original answer, and it's 1.999 recurring 6. That's not terribly accurate, but then considering we landed men on the moon using over 3 decimal place slide rules, I thought that was satisfactory from my point of view. I'm using Microsoft C floating point, which may or may not be causing me a problem. But I then did the same with square root of 3, which is 1.732, etc., and squared that again to get 2.9 recurring 6. I then moved on to something slightly more complex, and this is another thing that every schoolboy or schoolgirl knows. Roots of a quadratic equation. On the left, we have fixed variables A, B, C, and 4. 2 results entries, omega 1 and omega 2 are resultat. And the last 2 are robotchie, work locations. And on the right is the actual program as it comes from the original book. And that's the full program. Data and the actual instructions. I just pulled some values out of the air, 6x squared plus 17x plus 12, ran the program, and I got the answers from this program. First line is 0. That's a thing this program does. If the roots are real, it's a 0, and if the root's not real, it doesn't print anything at all. And the actual roots are minus 1.3 recurring and minus 1.5. And I ran this quadratic equation through a online quadratic equation solver. Happy to say I still got minus 1.5 and minus 1.3 recurring. Thanks to Math is Fun. Moved on to calculating E. I just allowed X to be 1 to be simple. As the program I created from the original text, and 2.71828, etc., etc., etc. So far, so good. I then did a bit of trigonometry, sine of X using a sine, well-known sine sequence. And sine of 45 degrees or 1.57 radians is, 90 degrees is effectively 1. Then there was this exercise for the reader. How about creating cosines using the formula square root of 1 minus sine squared. So I enhanced the original program, first of all, to allow me to put angles in degrees, and secondly, to calculate the cos using that formula. And also I then calculated tan by using sine over cos. So 45 degrees is 0.785 radians, and both sine and cos of 45 degrees is root 2 over 2. And then the tangent of 45 degrees is somewhere around 1.
Yeah, don't do that.
What?
It converge very slowly.
It does converge very slowly. And we run it on the witch.
Okay.
And it takes all day. Yeah, something like 7 decimal places. And this, as it happens, is the witch program that one of our volunteers wrote, which I then, feeling I should try and write some software that isn't in the book, converted to that, and ran it. And sometime later, it converges very slowly. This is after about 15 minutes running, I think, and you've got 3.14179 and 3.14139 being repeated over and over again. So thus far, I've implemented in this simulator these instructions: plus, minus, multiply, 2 different multiplies as it happens. Stop function, capital P for print, capital V, lowercase v for read cards, equals, not equals, less than or equal, absolute less than or equal, or square root function. And I thought I might as well use this print function to actually produce some visible output other than on the screen of my laptop. So that's the program for calculating pi. And this is my program running with a 2-line display connected, stolen from a retail system, connected to display the values. After it had run for rather longer, I might add. And finally, the Collatz conjecture, which I've been told I should never actually mention in public, because if it does, it completely destroys any mathematical credence that I might have had. But that's all right, I'm happy to play with it anyway. You think of a number, positive non-zero integer. If it's even, you divide by 2, so you end up with a value j, which is half of I. If it's odd, you multiply it by 3 and then add 1, so j is now 3i plus 1. And you loop back to 1 with I equals j. And eventually the conjecture is that no matter what value you start at, it will terminate with the last 3 values of 4, 2, 1. And the sequence is considered finished when it gets to 1. And the conjecture is that the sequence will always end in the same way, and no one's ever proven that it hasn't. And this had an interesting couple of functions because it needs you to know whether a number was even or a number was odd. And fortunately, there are 2 further functions defined in this language. Curly brackets n, which returns the fractional part of the number n, and square brackets n, which returns the whole number part of the number n. So that means you can now immediately do, does it end in 0.5 or up to divided by 2 or not? So I added the curly brackets and the square brackets, extract the fractional part and extract the integer part. And this is the program which I created pretty much from scratch to do that job. I started with a value 1, 2, 3, 4, 5, 6, 7. This is the card deck on the left. This is the value 1, which is finally achieved, 168421. And 111 is the number of steps that the conjecture ran for, the software ran for. And I ran that on an online French Collatz conjecture simulator. And indeed, for 1, 2, 3, 4, 5, 6, 7, I got a stopping time of 1. All so far, so good. And then enhanced my simulator to have a list of files which I can execute instead of having having to load programs in by renaming them to a common name, but that's not particularly important. And that's my program for simulating the pseudocode language in the first book. So just a quick rundown of what's in this program. Box number 1 is the name of the file and any commentary that goes with it, written in UTF-16 big endian, and why not? And then print readable, human readable characters. Box number 3 is the memory addresses, and box number 4 is the memory content. 5 is the actual software. 6 is the cards. 7 is tracing. And this program produces way more tracing than I would ever be able to read. You could never have enough tracing. And 8 is the result. 16, 4, 2, 1, and 1, 1, 1 for the count. And it also prints, because I had a pi, one of those pi's in the instructions, it also prints to a notepad file, fortunately in ASCII. Now, there's a couple of special features which are rather interesting. One of them is indexing, because if you're going to be having addresses, pointers to address, you need to be able to change the addresses. And there's this function, plus in a circle, a+1, beta, a+1. Now, you might think that plus in a circle means exclusive all. But actually, it doesn't. Plus in a circle means add a value to an instruction rather than doing anything exclusive or related. And this differs from adding a value to a data location. And I just did write a small program which is basically doing a list of squares, if I remember correctly. Yes. So the result of running this program, you end up with, by doing indexing into the workspace, 1, 4, 9, 16, 25, 36, 49, and so on and so forth. And down here we have a print box, which is also showing the same values. There's also a minus sign in a circle for subtracting a value if you want to do an index in the reverse direction. Then we come to subroutine handling. And there are 3 orders which are involved in subroutine handling: BP, BPP, BPRV. And this is an example from the book of how you do subroutines. Now, A, B, and C, the sort of boxes on the left, are parts of the main program, and the subroutine you're calling is Q. And what this is doing is basically modifying using the values gamma1 and gamma2, which are branches to p+4 and p+r+7. There will be a test. It modifies basically the last instruction of the subroutine at p+2. So the subroutine can then return to the next part of the main program, and then the same thing is done when the subroutine is called again. Little test program. Oh, and of course it works. It's very easy to make things work when you're writing the simulator as well. Yes, sir.
If you're in floating point, does it simply truncate the floating point value and use that as the integer value to add?
For
indexing.
Oh, for indexing, as far as I know, they're integers. But for indexing, for adding values to the
So it treats the bit pattern as an integer rather than a floating point.
That's an interesting question, actually. Yes, it's going to be an integer followed by a decimal point, followed by all zeros.
The same question,
Yes.
with your rounding, you're taking the integer and fraction part.
Yes.
If it's floating point, there's a risk that it might go wrong unless you add a half to start with.
Yes.
Yeah.
So how many bits in the floating point and how many in the integer?
Well, it's in the Microsoft float doubles.
No, in the Russian computers.
Well, this isn't actually a language for a Russian computer. It's a method of writing and demonstrating how you could write programs to run on a Russian computer. When I get to the KIEV, I can answer those questions in more depth,
So the language doesn't actually specify how many bits that's in.
because they'll be different for different computers that it's
Okay.
referring to. Now, this routine, this methodology works perfectly well. But some of the machine have subroutines hardwired into them, either hardwired into the actual computer box or in plug boards. And obviously a program can't go around moving the wiring around to change the change the return addresses. So the second option, which is rather more simple, in fact, the BPP function calls a subroutine, and it also uses it also introduces a return address link register, so that the subroutine then can just use a function BPRV to return. BPRV jumps to the address contained in the return link address register, which I then added the return register into my emulator at this point. So that's covered indexing, and that's covered subroutine handling, and that's the full functionality in my simulator that now exists. So I've added the adding to the addresses, subtraction to addresses, the subroutine calls. And also there's a reverse B function, which I had a lot of trouble finding in the Unicode collection for a halt instruction. But it's effectively the same as the OCT function higher up the list. Incidentally, some of the names I've given French names to as well from the French version of the book. So OCT, which is stop, is ARR, in French, which is just arrête. Moving on to a real computer now. I was pointed at this book here, which is the calculating machine KIEV, a mathematical explanation. It's in Russian again, even though it's a Ukrainian publication. Fortunately, there's an actual English translation available for this one, which made it does come with this caveat. It's not been edited to refine or improve the grammatical accuracy, syntax, or terminology. And also it introduces a few errors, which I do nevertheless have to refer to the Russian version when something doesn't make sense in this English. Now, this machine has 41 bits in a word, which is rather a lot of bits for a computer of that age, in my opinion. And these 41-bit words can be used for two functions, either holding a number or incorporating an instruction. So when it's a number, you have 40 bits of bits forming a number, and the first bit is the sign bit. And note, this is a fixed point, the decimal point before or between bits 40 and 140. So every number is less than 1. And it does not, when you negate a number, it doesn't use 2's complement either. And an example from the book is hardwired address 3035 contains 17 or all the other 7s, which is 1 minus 2 to the minus 40, which is the closest you can get to +1. And location 3036 contains 3 7 and all the 7s, having turned on the 41st bit, and that's minus 1 minus 2 to the minus 40, which is the closest you can get to -1. This adds the interesting feature, which I think the Which has as well. You can also have a +0 and a -0. I see a nod from the corner over there, thank you. Now, the same 41 bits can be used to hold an instruction. And what you have in this case is you have the first 5 bits hold as an operation code. The next 12 bits contains a modification indicator and then 11 bits of an address. And then the next 12, the same as the first 12, and the next 12 is the same as the previous 12. So if the modification indicator is 1, then it means it can add values from a modifier register to the address being referred to. There are also various subroutines, again, hardwired into the machine. So, for example, at address 3163, you have a square root function, which looks like that. And you can see that the leftmost column is the address 3163, 4567. Now, all this is in octal. 3163, 4567, and 1. The functions are 5 bits in 2 octal digits. 01, 12, 02, 11, 01, 05, 32. Then you have 3 addresses, all of which are in octal. I got an awful lot of this from the GitHub software package, which I found, which I was pointed to GitHub, and I am using this freely as I have their permission to do so. The works of Olha Lyuba have been very useful. Dziękuję wam, Olho. So instructions are 5 bits. First instruction is 00, which is just a null function. It counts as a null, it just chops through. 36 and 37 are illegal. Then there's 2 variants, then there's an arithmetic add, 2 variants of subtract, 2 variants of multiply, divide. It's got a fairly complete instruction set. The 2 variants of multiplication are with rounding and without rounding. If you multiply 2 40-bit numbers together, you really need an 80-bit register to put the answer in, but there doesn't seem to be one. So you can either round when you truncate, when you throw away the last 40 bits by adding 1 to the first bit that you're throwing away, or you need not do so, depending on whether or not you want the answer rounded. And there's others adding to an order, cyclic addition, which is effectively a kind of rotary shift. And then there's AND, OR, and XOR. And various jumps, less than equals referring to absolute values, equals, and less than or equals minus 0. Subroutine calls and returns, shifts, logical left and right, and group operations, which are rather interesting because they're like for loops in C terms. They're actually implemented in the hardware. And then there's device control instructions, input, output, trump storage, and I haven't really gone into those particularly because I don't plan to try and emulate the hardware devices. Now we come to the refresher on the address programming language. Now this is the jump if less than or equal to function, SR1. And they then explain how this function works using the address programming language. So, first character is a P. It's a Latin P, not a Cyrillic R. And that is used to abbreviate the word predicate. A predicate is basically an if statement. So it's saying if the contents of A1 plus if E1 is 1 times the multiplication register is less than the contents of A2 plus the index register, the modification register, and the contents of the modification register. And then the curly bracket here, there's a curly bracket at the start after the P and a curly bracket at the end after the just here. Yeah. There. Then the third address, including any modification value, is put into C, where C is the instruction address register. Otherwise, it just adds one to the current instruction address register and puts it in the instruction address register.
So,
And then all these functions end with double prime C goes to K, where K is actually the instruction register as opposed to the instruction address register. So that's the instruction it's going to execute next. So this is a slightly more detailed way of looking at it. I'm just pointing in the predicate you have A1, which is the 11 bits here, A2 and A3, and you have the modification register E1, E2, and E3. And this is a list of all of the registers in the machine, and I haven't actually tried to implement all of them, and I'm not going to explain all of them today, but C is the address of the current command. K is the actual register that contains the order that's going to be executed. A is the modification register, whose value is added to addresses if the appropriate bit is set in the address field of an instruction. And TB, the last one on the list, the original Russian for this is tumbler, which does remind me of an English word I haven't heard for a very long time, which is a tumbler, as in a tumbler switch, which is terminology which I seem to remember from post office telephone exchanges or something. Mm-hmm. So there is a switch you can turn on and off, which modifies the behavior of the add instruction. So first of all, if you're adding to the contents of two addresses, you carry out the first line. So the contents of A1 plus any modification plus the contents of A2 plus any modification go into A3 plus any modification. Now remember I said that all values are less than 1. So if predicate, the result in the address 3 is now greater than equal to 1, which logically it can't be, but I guess it knows somehow that it could be, then it goes to the next line. Otherwise, it just goes to the next instruction. If the next line now has the tumbler switch on, then it jumps to the instruction +1 after the regular instruction it would have gone to. And that is, they explain, to be able to take care of any scaling you might want to do. So if you get this error and it goes to the second instruction, you can rescale your calculation. And then once again, double prime C goes to K. So whichever one of the values was written in C here now goes into the order register. And that's just a repeat of what I just said. So I don't need to repeat that, do I? And so that's the complete function explained in address programming language. And I've already really gone through it step by step. So we can skip. There's I mentioned there were two interesting multiplication registers. And I did say that one of them is multiplying two 40-bit numbers, and if the number's too big to fit in a 40-bit answer, then you can do either no rounding, which is the top option, and the bottom option is with rounding. And it doesn't actually say with rounding in any of that text. It just says this is much the same as the instruction above. Mm-hmm. But actually elsewhere in the book, it does explain that rounding is involved. So this is a second simulator which I've now put together, which actually runs so.
When you say rounding, does it round to 0 or round to infinity?
What it does is if you've got you multiply two 40-bit numbers, and you get an 80-bit answer, from the 41st bit, counting from the left, is then has 1 added to it.
It runs to infinity.
if you say so.
Well, it depends on, it's complicated over the fact it's not a two's complicated machine, but you're right, it's, yes, it's towards plus infinity, yeah, towards infinity.
Right, so I now have a program that runs most, maybe 2/3 of the instructions that the KIEV machine can run. There are other projects going on, I must add, which I found on GitHub in various places, which are a Ukrainian gentleman who attended the Tony Sale Awards program event told me about. I've written, you're right. So I have a few, when I'm writing emulators for these programs, I tend to write them in standard C as well, so I can compare the answers to make sure that the execution of the instructions is working. So I have a square root and e to the x just available in straight C. I have 3 languages available: Ukrainian, English, and Russian. The text in the middle says in effect JM, which is my initials, and then KIEV, which is the name of the computer in Ukrainian. I have initial program load, which basically clears the memory and then loads all the hardwired subroutine. Single step button, the run button is to say that until I've loaded something. And then if I want to break into a loop, I can hit the break button. Load allows me to load programs from external files. And then the tumblers, and the X is for exiting the emulator. And again, I've got some data a bit that shows the trace of the instruction having been executed, the name of the program being run, and the main memory. And then there's some other interesting register values: the link, the loop, which is basically a loop counter, the modification register, and of course the address at which it's got, and the address of the instruction has been executed. Now, this book also comes with some interesting programs to try and emulate or demonstrate on the machine. This looks kind of scary, but it's not as well, it looks scary to me, but it's not as bad as it seems. And I was able to convert this collection of instructions, data and instructions into programming language for this actual computer. And it runs. And when it's done running, it stops. Then the final thing which I'm going to show you is the use of the square root function, which again is there, and also a function to convert a binary into decimal. It's another hardwired instruction, so it's actually on either a plug board or hardwired into the machine. And it's remarkably short. It involves loops and so on. And I plan to demo that with luck. Stop sharing. That's got a chance of being the right thing. So, first thing I'm going to do is I'm going to do the initial program load, which clears the memory and loads all the hardwired instructions. Like so. So most of the memory is zeroized. Oh. And then I'm going to load a program which is called square root plus binary to decimal, subprograms, big programmer 7.1. And there they are, subprograms 7.1. And I will just step for a couple of instructions. So up here, we've now got some information about the program, the program instruction that was just run. So it was a zamnoj, which is multiplication with rounding. Multiply 3055 by 3055, put the result in 2. Another instruction. And then that's a DOD, a DOD, add instruction. And in fact, this you can see is adding 0 to 0, which is the way they clear a location, location 3, workspace 3. Now we have another DOD. So let's just run the program to completion. Like so. And what it did was it squared 2. And then took the square root of 2 and converted it into binary coded decimal. So I sent it to my virtual printer. I squared 3 and then took the square root of the product and printed the result of that to my virtual printer. And that, I do believe, is that.
Okay.
Seem to have lost the last page of my slide. Not to worry. Are there any questions? Yeah, Patania.
Thank you.
You're welcome.
Yes, a couple.
Go ahead.
Well, you started off by saying things start at 1, not 0. My immediate reaction was, naught's where the subroutine link goes. But then you proceeded to demonstrate it wasn't.
Yes.
That was interesting. You haven't answered the question, why does it start from 1?
And I don't know the answer.
Okay, fair enough. Maybe people start counting from 1, you know.
Yes.
What we used to before computers. The second one, right at the end, I saw that list of functions. And I was fascinated to see a half sine and a half cosine and so on.
That's because you can't have a whole value.
Well, it's more than that because you slightly twist the routine not to give the whole value. And I've known people do that. But then when you come to do a sum and difference formula, like sine A, sine B plus cos B, cos A, even if you distorted the basic function not to go beyond just under 1, that equation could go just over 1. So it's better to always deal in half values.
Yes.
Yeah, exactly, yeah. Look at the Elliot 903, it's got a separate subroutine link, and well, it's got no subroutine instruction, no stack. That's exactly what you've got there, no stack, you put the link somewhere specific.
Yes.
Yeah.
At the ends of the functions, in fact.
Yes, fascinating.
Somebody, Rob Schofield has just messaged in saying that Intersil and AMS microcomputers also use address indexes beginning at 1. And so does the SC/MP processor. As a software man, you don't understand a word of it. Some of you might.
So you showed us a square root routine. But in your later example, you used square root. But you weren't doing a subroutine call there, you were using the hardware square root, were you?
Yes, yes.
Hardware, yeah.
Because I was looking for the subroutine calls and couldn't see one.
Yes.
I've just been looking at the GitHub emulator. And it would seem that it's a group of female students at the Ukrainian Catholic University that's responsible for it. So that puts me in mind of Kateryna, Kateryna's life. Do
Yes.
you know anything about the context in which she worked?
Yes, but I know she was working with those other 2 co-authors. I'm actually in contact with her son. Possibly you are. You seem to know more.
No,
You
not
seem to
at all.
know stuff about
This
this now.
is me.
She's, well, I don't know the details, but I've seen various family photographs and things like that. But, I haven't been exposed to the details.
Max Hughes has typed in a message saying, any idea of the physical size of the KIEV computer? Is it this room, the meeting room next door?
It's probably going to be this room, I would think. I have seen some photographs of a computer called the Minsk, capital of Belarus, I believe, and it was installed in a church. Yes, in Soviet times. And that was certainly a this room-sized computer. I imagine the Kiev is going to be something similar.
Yeah, I think from the researchers from Science Museum looking at the physical remains of some of the computers, a lot of them were air cooled and therefore just took up a lot of space to get the volume of air through the cabinets.
Incidentally, I should mention that I did bring a couple of the books with me in there. The Kiev. I didn't bring the English translation. I thought some of you might like a challenge. This is the Dresnoye Programowanie, also in the original.
Well, they certainly seem to pass the spring balance test in terms of manuals.
Yes. And the American translation of this is actually slightly thicker than that. That's just down to font sizes and things.
Interesting YouTube video, sorry, Rob Schofield, video describing the fixed point 45-bit multi-unit processor called the Woodpecker. And he gives a link
I guess.
to the YouTube video.
Well, I don't know what the Dugar woodpecker is.
Hmm.
Do we know in which application area the Kiev was used? Well, actually, no. I have to say, I don't.
Do you know how many of these machines were built?
I imagine, yeah.
Suggesting it was over the horizon radar.
Okay. Okay, so this was kind of the era when people were making one EDSAC and one Witch, and probably, I would guess, one Kiev and one Minsk and so on.
Just an observation, really. You remarked at first the superscript with the number indicating multiple dereferencing of a pointer, and then observed you can have a negative or effectively a search through memory.
Yes.
This is actually implemented in APL, or at least that some of the APL-like languages. Obviously not over the entirety of memory, which would be a nonsense.
Which APL?
Well, I'm thinking of K, but I believe
The other APL.
Oh, the real APL, not well.
yes. Oh, sorry. Yes.
Not this address programming language APL, but the A programming language, wasn't it?
Only 5 years later, well, 7 years later.
You mentioned right at the beginning of the talk, BESSM at the Science Museum.
Yes.
My understanding is that when it was rescued from its original home, all the parts were carefully assembled and brought with the intention that it possibly could be restored and made to run in the future. But obviously nothing has been done towards that, and it's probably unlikely that people will be now giving Science Museum's sort of general policy on restoration and running of hardware.
They might like to lend it to us to make it.
It's quite large.
Yeah, I've seen it, yes.
Philip Wardle has observed that the woodpecker may be a reference to jamming high frequency over the horizon radar.
Oh, yeah.
We were listening to this in Marconi in the late 70s, as we anticipated having to deal with it in our own radar designs at the time. And Stephen Kessler has asked which institute organization built the Kiev computer. Was it a particular university? Or he does also ask whether several versions built, but again.
As far as I know, there was only the one.
Yeah.
But where it was built. It says somewhere in there that who actually built it, but I don't have my hands on the reference immediately.
Yeah. A lot of these things, as we were talking about things like the Harwell Decatron and so on, they were built for specific purposes, by specific organizations. Well, nothing else coming in on the chat at the moment.
Anyone else in the room? Well, Jerry, thank you very much indeed.
Welcome. That's the meeting.
Well, thank you. That was really interesting, and we all now need to brush up our Russian so that we can also
Spasibo.
learn to use the APL. Really interesting presentation. Thank you very much indeed.